In this video, we're going to introduce the basic concept behind Shellsort. As an FYI, Shellsort is hard to understand, okay? Like, really hard. I'm not going to ask you to trace this by hand, it's a pain, okay? Just FYI. All right, so here's a thought. Thinking about insertion sort for a second, let's think about, maybe something that's a bad input. So taking a look over here, I have this input here, which is 8, 2, 3, 4, 5, 6, 7, 1. Okay, clearly unordered. We want to sort it somehow. Okay. So first question there is how many inversions? Well, 8 is out of order with everything to its right-hand side, right? So that's going to be, what, 7 inversions there. Plus 1 is out of order, everything to the other side. So another 7 inversions there. How many inversions how many exchanges would insertion sort require to sort this? Well, insertion sort, it's basically going to take the same number. So insertion sort, if an array has, n number of inversions, typically what that means is insertion sort has to do that many exchanges in order to fix it. So actually right over here, right, this is, 14 inversions implies basically 14 exchanges in terms of insertion sort. That's a little bit bad. So what do we do? Well, working on my paper, I could do a little bit better job, right? If I look at that, I should be able to exchange 1 and 8, right? And all of a sudden, I have my, my 1 over here, my 8 over here. Everything's, done, right? I do just 1 exchange, and it's sorted. Okay, that's actually kind of nice, right? So how do we get there, right? So here, right, we're saying is that, insertion sort maybe would have 14 exchanges, whereas if we did this on paper, we could do it in 1. How can we make it better? Is there any way maybe we could enhance insertion sort to get this better performance? And the answer is, of course, yes. And it leads us to the idea of Shellsort. So Shellsort is basically a variant of insertion sort. In Shellsort, we basically do it's basically just insertion sort, but with the introduction of a gap. So normally in insertion sort, we compare elements that are back to back, right? So it's like we have an array of A, B, C, D. We compare A and B. We compare B and C. We go by pairs that are right next to each other. We go by neighbors. In Shellsort, the difference is we have this gap value, and this we call it H. H is basically our gap size. So here H equals 13. So instead of comparing, for example, P and H, we compare P and S, which are different, right? That's 13 elements in between, okay? The idea is long-range exchanges do us more good. So that's what I started to see on the previous slide, right? So if we do local exchanges, right, we would swap 1 with 7, 1 with 6, 1 with 5, 1 with 4, 1 with 3, 1 with 2. We have to swap all those different times. Those are all local changes. If I thought about doing a global exchange, if I thought about taking things to the end and move it all the way up to the front in one go, then I've done more work. I'm closer to having a sorted array. Well, what we can do is we can try to encapsulate that in the process of introducing a gap, right? So we say that, okay, I'm going to compare the beginning of the array to the end of the array, and then I'll do the comparison, move the smaller thing forward. The hope is, right, is that's kind of cost effective, right? So I do one exchange, I do exchange with a gap in between, and so if those two things are out of order, right, hopefully I'm moving that one thing from the right hand side, moving to the left. I'm basically saving a bunch of exchanges that I normally have to do in that middle region, right, in order to get all the way to the left hand side. So I'm kind of trying to find the things that are most out of order first, fixing them, right? So yeah, that's the basic idea, right? Move things that are far away first. And then what happens in the end, right, is we have to shrink this down. Because if I just do everything and compare it 13 units apart, well, then it's not going to be sorted. It'll get a little bit better, but it won't be fully sorted. So what I have to do is I have to basically work this down. So here I went from 13 to 4. So all of a sudden, the idea is make your gap smaller and smaller and smaller and smaller. Start comparing things that aren't so far away. Start comparing things that are a little closer, a little bit closer, a little bit closer, a little bit closer, and you start to converge to something that looks more sorted. Eventually, you get down to basically a gap of 1, which is insertion sort itself. Basically, you're saying that we're going to start with insertion sort, but comparing things that are very far away, and then shrink it, until we get to the insertion sort itself, and just run insertion sort normally. And hopefully, by the time we get to running insertion sort normally, basically everything's where it needs to be. It should look like something that's like a nearly sorted array, because that's the type of thing that insertion sort can process really, really quickly. All right. Let's see. Actually, let me just highlight this note here, right? So somehow what happens with the gaps Is if you introduce the gaps and you kind of start sorting it, in terms of these distance things, what you're basically saying is, oh, after I do this operation here, this is actually, we call it an array 13 sort or 4 sort, right? There's actually some terminology when we're doing this gap-based insertion sort. If we sort by some value k, we say it's k sorted. So if I say something's like 13 sorted, somehow what I mean is that there's not going to be, there's not going to be stuff that's too far away, right? Something is going to be, something should be at most 13 positions away from where it belongs, right? And then when I do a 4 sort, right? It should be most 4 positions away from where it belongs. Roughly speaking, the goal is, right, is that things are kind of converging to where they're supposed to actually be in the final sorted result. All right, so that's our basic idea for shell sort. I know it's a little bit tricky, but just think to yourself, right? It's insertion sort, where instead of comparing neighbors, you compare things that are far away. And then you eventually shrink that gap, shrink it, until you get just to insertion sort.